So after a short break, we will continue our question paper, question 2b1. Let's question 2b1. Determine whether the given set of vectors S is equal to 1 plus x, x plus x square and 1 plus x square is linearly independent or linearly dependent. Now we want to check that these three polynomials 1 plus x, x plus x square, 1 plus x square, these three polynomials of P2, right, is linearly independent or linearly dependent. Now to prove that the given set of vectors or the given set of polynomial is linearly independent or linearly dependent, what we have to do? We have to use determinant method. Why we can use this method? Because of these three polynomials are the polynomials of P2, and dimension of P2 is equal to 3, and we have exactly 3 polynomials. So that's why we can use determinant. Okay, that's why we can use determinant. For linearly independence or linearly dependence, one thing that you have to remember that if you have set of vectors of vector space V, right, and if you have more than the dimension of vector space V, more than vectors, the dimension of vector space V, so that set is always linearly dependent. What I am saying to you, that if dimension of V is equal to n, right, if dimension of V is equal to n, and if our set S, let's take capital S, if you have n plus 1 vectors in S of vectors of V, then you can directly say that that set S is linearly dependent, because you have more than vectors than the dimension, that set is always linearly dependent. As for example, we know that dimension of R3 is equal to 3. In general, dimension of Rn is equal to n. So dimension of R3 is equal to 3. If you have set S such that S contains 4 vectors of R3, S contains 4 vectors of R3, and dimension of R3 is equal to 3, S contains 4 vectors of R3, so that set S is always linearly dependent. You don't need to you don't need to check that one. You can directly say that S is linearly dependent. Okay, right, exactly. Now, but if we have same number of vectors such that dimension as dimension, then you can check the determinant method. Okay, same thing happen here. Dimension of P2 is equal to 3, and we have 3 polynomials of P2, so that's why we check that determinant method. The first row is the coefficient of first polynomial. First one is constant 1 plus x. First row is for 1 plus x, so constant term is 1, coefficient of x is 1, and the coefficient of x square is 0, so that's why first row is 1 1 0. Second row is coming from the second polynomial x plus x square, so that is 0 1 1. Third row is coming from the third polynomial 1 plus x square, so that is 1 0 1. Okay, so now you can easily check, you can easily try to find the value of that determinant. Okay, so 1 1 1 0 0 1 1 and 1 0 1, that is equal to 1 into 1 minus 0 minus 1 into 0 minus 1 plus 0 into 0 minus 1, so that is 0, so that is equal to 2. If you will get the value of determinant is non-zero, that set of vectors are linearly independent. If the value of that determinant is equal to 0, that set of vectors are linearly dependent. So here we get value of determinant is non-zero, so that's why the set of vectors S is linearly independent. Okay, so this question asked in 2 marks, and this question is complete now. Now next is question 2b, second part. Question 2b, second part. Determine whether S is equal to a0 plus a1x plus a2x square plus a3x cube. a0 plus a1x plus a2x square plus a3x cube, where a0 is equal to 0 and ai belongs to R, where I is 0, 1, 2, 3. So all the coefficients are real numbers, where a0 is equal to 0, is a subspace of P3. Now what type of polynomials S contains? Try to understand first of all that one. Clearly S is a subset of P3, where P3 is a set of polynomial, but what type of polynomial contains S? What type of polynomials S contains? That I want to explain you, that such polynomial of P3 such that constant term is 0. Constant term should be 0. That means there is no constant term. Directly the coefficient of x, the coefficient of x square, and coefficient of x cube. Okay, so that type of polynomial are in this set. So let Px is equal to a1x plus a2x square plus a3x cube, because belongs to S. Okay, and Qx is equal to b1x plus b2x square plus b3x cube, belongs to S. Okay, so let Px plus Qx is equal to a1 plus b1 into x plus a2 plus b2 into x square plus a3 plus b3 into x cube, belongs to S, and alpha into Px, that is equal to alpha into a1x plus a2x square plus a3x cube, that is equal to alpha into a1 into x plus alpha into a2 into x square plus alpha into a3 into x cube, that is also belongs to S. Okay, now to prove subspace, what we have to prove? We only need to prove these two conditions, that if you want to prove that S is a subspace for any vector space V, we consider any two vectors from that set and try to prove that addition of that two vector is also belongs to the set. And then for scalar multiplication, for any alpha belongs to R and x belongs to V, we prove that x belongs to S, we prove that alpha into x is also belongs to S. Exactly we prove that two conditions here. We are starting with P and Q, any two vectors belongs to S, and we prove that Px plus Qx is also belongs to S. We are starting with any alpha belongs to R and Px belongs to S, we prove that alpha into Px is also belongs to S. So that two conditions are satisfied here for subspace. Okay, so that's why this two that's why this set is a subspace of P3. Okay, so next condition, next question. Question 2b, third part. This question asked in 3 marks. Determine whether the given vectors v1 is equal to 1, 1, 1, v2 is equal to 0, 1, 2, and v3 is equal to 3, 0, minus 1 form a basis for R3. Now here we use one important theorem such that our example become very easy. Okay, why? See, what is the definition for basis? B is a basis, or S is a basis. S is a basis for vector space V if first condition S is linearly independent, and second condition S spans the vector space V. But using this example, using this statement of this theorem, which is written in the solution, in the front of the solution, you can easily solve this example. What is it? See, if dimension of V is equal to n and S contains exactly n vectors, okay, if dimension of V is equal to n and S contains exactly n vectors, then S is a basis of R3. S is a basis of R3 if S is linearly independent or S spans V. That means what? Using the definition to prove basis, we have to prove these two conditions, that S is linearly independent and S spans V. But if we have such properties that dimension of V is equal to n and the given set is also contains exactly the n number of vectors, then you only need to check one of the conditions, either S is linearly independent or S spans V. And to prove S is linearly independent, it's quite easy. We already proved one example before this example, right? So to prove S is a basis for vector space V or not, we just need to prove S is linearly independent or not. If S is linearly independent, S spans V automatically, and that's why S is a basis for R3. That is our aim. Okay, so I repeat this theorem. Let S is equal to V1, V2, V3. Here we use one theorem, that if dimension of V is equal to n and S contains exactly n vectors, then S is a basis of R3. Same thing happen here. You can see this, all of three vectors are dimension of R3. All of three vectors are from R3. So dimension of R3 is equal to 3. This set S is contains exactly 3 vectors. So that's why you don't need to prove S spans V. Just we prove that S is linearly independent. So S spans V automatically. S spans R3 automatically. And so that's why S is a basis for R3. Okay. So just here we only need to prove that S is linearly independent. And for linearly independent or dependent, we use determinant because of number of vector and dimension are same for vector space, right? So the first vector is 1 1 1. So first row of the determinant is 1 1 1. Second row is coming from the second vector 0 1 2, and third row is coming from the third vector 3 0 minus 1. Just solve this determinant. 1 into minus 1, minus 1 into minus 6, plus 1 into minus 3. So minus 1 plus 6 minus 3, that is equal to 2. So the value of determinant is non-zero. So that's why the given set of vectors are linearly independent, and S is linearly independent. So S is a basis for R3 using the previous theorem. So this question number 2 is complete now, and now next question number 2 or question 2 or question 2b or question 2b. In this question paper, just try to understand how its paper style. Question 1 is compulsory. Question 1 ask in 14 marks total. Question 2a compulsory. Question 2a ask in 7 marks. Okay. And now your option is coming from question number 2b. Question 2b or question 2b. So first question 2b is complete now. This is or question 2b, right? Question 2b 1. Determine whether the set of all functions f such that f of 0 is equal to 0 is a subspace of the space capital F from minus infinite to infinite. This question asks in 2 marks. Again this question asks of a subspace. So what we have to prove? We prove two conditions, that if f and g, here our set is set of functions, right? Our set is set of functions such that f of 0 is equal to 0. So we take any two functions from the set and try to prove that addition of that two vector is also belongs to the set, and scalar multiplication is also belongs to the set. Okay. So let fx and gx belongs to capital F from minus infinite to infinite, where f of 0 is equal to 0 and g of 0 is equal to 0. So f plus g into x is equal to fx plus gx, that is equal to 0 plus 0, that is also is equal to 0. And the second condition is also satisfied quite very easily. So this question is complete now. This set is a subspace of R3, f from minus infinite to infinite. Question 2b, second part. Verify Pythagorean theorem for the vectors u and v, where u is equal to 3, 0, 1, 0, 4, minus 1. Okay, and v is equal to minus 2, 5, 0, 2, minus 3, minus 18. Right? What is Pythagorean theorem? In Rn, state that if x and y are orthogonal vectors in Rn, then norm x plus y whole square, that is equal to norm x square plus norm y square. Okay, norm x plus y whole square, that is equal to norm x square plus norm y square. Right? For the given vectors u and v, inner product uv is equal to u dot v. Now we try to check that these two vectors are orthogonal or not. Okay, so that's why we check inner product uv, and now inner product uv is equal to u dot v, because we use Euclidean inner product. So u dot v, that is equal to 3, 0, 1, 0, 4, minus 1, and minus 2, 5, 0, 2, minus 3, minus 18. So just simply dot product 3 into minus 2, that is minus 6, plus 0 into 5, that is 0, plus 1 into 0, that is 0, plus 0 into 2, that is 0, plus 4 into minus 3, that is minus 12, plus 1 into minus 18, that is plus 18. Now you can see minus 6 minus 12 plus 18, that is equal to 0. So it's correct that these two vectors are orthogonal. Okay, now if these two vectors are orthogonal, this Pythagorean theorem should be satisfied for this two vector, and that we have to verify. Okay, so norm u plus v. Now first of all we have to find norm u plus, first of all we find norm u square and norm v square. Okay, and it's quite easy, because we know that for any vector u, if u is equal to, if suppose take u is equal to u1, u2, u3, norm u square is equal to under u1 square plus u2 square plus u3 square. Okay, so norm u1 u square is equal to 3 square plus 0 square, because